In this video, we'll be discussing enzymes, which are a particular type of protein. Enzymes are extremely important in the regulation of the metabolism of all living organisms. The first term that I'd like to discuss is called a catalyst. And a catalyst, it explains the role that all enzymes do. They are a substance that alter the rate of a chemical reaction without the catalyst itself being changed or used up. So what this means is that as enzymes utilize their function, which is to lower reaction rates and to regulate metabolism, they can be used over and over and over again without losing their function. Enzymes are a special type of protein that, as we stated before, act as catalysts in all cells. There are three specific roles that enzymes have. The first role is that they speed up all chemical reactions by lowering their activation energy. We'll talk about what activation energy is in just a little bit. Their second function is to allow reactions to take place at lower temperatures. And the third function is to regulate metabolism. When you speed up chemical reactions and you allow reactions to take place in lower temperatures, that is the act of regulating metabolism. So what we have here is what we call an activation energy graph. It looks pretty confusing, but once we start to break it down, it really should make a lot of sense. So over here on our y-axis, we have what's called free energy. So what that means is the higher up you go on this graph, the more energy is being used for a chemical reaction to occur. On the x-axis, we have progress of the reaction. So this is our time. As we go farther over this way, that just talks about how much time the reaction has taken to take place. Now we have two separate lines over here. This red line represents a chemical reaction that has happened with an enzyme. And this black line represents that exact same chemical reaction happening without an enzyme. So for all chemical reactions, as we talked about in class, we have our reactant side, which is the beginning of any chemical reaction. And then once those reactants react together, we will then form our product. Now it's important to keep in mind that in this graph, you're comparing the exact same chemical reaction. The only difference is that the red line represents an enzyme that's present and the black line represents no enzyme present. So let's look at the black line first. If we look here at this black line, we'll notice that the black line and the red line are starting at the exact same reactant point. What that means is that there's the same amount of energy that's needed for both the reactions to happen prior to the enzyme becoming part of it. So there's nothing here that's changed. But once those reactants begin to create bonds or make bonds, whatever the reaction is, we'll notice a really vast change here in the energy. This black line goes very, very high. And at this tip here, at this point, I'll make a little star up here, okay? This is what we call our point of activation energy. And I'm just going to put AE for short because this is really hard to write. Okay, so up here, this is our point of activation energy. And this is a very, very high point. Remember, look what our axis is. This is energy over here. So the higher up we are, the more energy that's being used. So in this chemical reaction, we're starting at the same point as we would if we were to have an enzyme, but we don't because we're following the black line. This black line will go up. We have a very high activation energy, and notice how it drops very fast, and then we have our products ending in the exact same spot. So what this is telling us is that this chemical reaction took a lot of energy to get this reaction done, okay? Now let's move on to the red line. The red line, as stated before, is starting in the same reactant point as the black line, but if you'll notice, our point of activation energy is much lower as it was in the black line. What this is stating is that because there's a presence of an enzyme in this particular chemical reaction, the enzyme has lowered the activation energy, which means that this chemical reaction, which is the exact same reaction as the black line, is doing the exact same job, but it's doing it with less energy because this line is representing that it's much lower, and it's also happening in a faster amount of time. Remember, our x-axis down here is representing time because it's progress of the reaction. And look how much less time we have. At this point, we are much lower than we are right over here. Oops. It's not a straight line, but you can see what I'm doing here. Okay? So not only does the activation energy get lowered with enzymes, but the reaction speed is also increased. And that's what enzymes do. In order to maintain metabolism, you have to have a certain rate of chemical reactions. If chemical reactions don't happen at a certain speed, then that particular organism will not be able to live. So enzymes are extremely important. If your chemical reactions happen too slow, you have the potential of becoming sick and, not being able to get the materials that you need, things like the exchange of oxygen or the exchange of sugars. They have to happen pretty fast. So there's so many enzymes in our body. The liver is the #1 organ that has the most amount of enzymes, but all of our organs have enzymes, and all of our cells have enzymes. And what they do is they ensure that all of our chemical reactions will happen at a rate that allows that organism to maintain homeostasis and to maintain and regulate its metabolism. These two terms describe the way that enzymes actually work. So what we have here, the term substrate. A substrate is not part of an enzyme, but it's the substance that's affected by the enzyme. So pretty much it's going to be the reactant of the chemical reactions. The active site, which is down here, is a certain shaped spot that's on the enzyme that can only bond with a specific substrate. So if the shape of the substrate is a square, the shape of the active site must also be a square in order for it to fit perfectly. The relationship between active sites and substrates are like a lock and a key. If the key and the lock don't fit perfectly, the enzyme is unable to do its job. This picture describes how enzymes are able to help chemical reactions move along with the help of that substrate. So here we have, here we have our substrate. Our substrate here in this particular case is going to be sucrose. Okay, so here we have a molecule of sucrose. And what's happening here is we have a hydrolysis reaction, right? Because we're taking a polymer, which is sucrose, and we are breaking up those covalent bonds and breaking them up into two separate monomers, glucose and fructose. So here, not only are we showing that we have this enzyme doing its job, but we're also incorporating and showing that proteins, because enzymes are proteins, are able to work with and that they need other macromolecules such as carbohydrates, right? Because sucrose, glucose, and fructose, these are all carbohydrates. So all these macromolecules work together all the time. They're not separate. They're constantly working together, which is so important that you have all of these in your diet. But anyway, I got a little sidetracked. Let's go back and talk about the process of the enzyme. So the first step is for the enzyme, which is this purple blobby thing over here, okay? The enzyme needs to bond with the substrate. Notice how our active site, which is right over here, is perfect shape, lock and key, to bond with our sucrose molecule, which is our substrate. So the substrate and the enzyme will find each other, as we see here in stage 2. It bonds perfectly. Once we have that lock and key fit, that's when the chemical reaction is able to take place. So notice here, because it is a hydrolysis reaction, water is going to enter. Water is going to break this covalent bond over here. Notice how the covalent bond is not here now. The enzyme will physically manipulate the substrate. It's going to put, in this case, because it wants to break it apart, it's going to physically move the two portions of the sucrose molecule and break that bond apart, and also utilizing water in there. And it's going to manipulate those bonds. So now we have our final product, which is 1 molecule of glucose and 1 molecule of fructose. Once the reaction is over, the product is going to float away, and it's going to perform whatever function it needs to perform at the time. The enzyme floats away as well, tries to find another molecule of sucrose, and it can start the reaction all over again. So this is an ongoing process. It finds the substrate, bonds with it, does what it has to do. In this case, it's breaking bonds. There are chemical reactions where enzymes can make bonds too. But anyway, so you have your enzyme finding your substrate, breaking or making bonds. The product is released. The enzyme is released. Remember, because it's a catalyst, catalysts are able to be reused over and over and over again. This same enzyme can do this over and over and over again. And that's how it allows chemical reactions to speed up, because it's helping the chemical reaction and what it's supposed to be doing. It's helping the water find the bond in order to break it. It's allowing this all to happen faster. There are 2 ways in which enzymes are able to catalyze chemical reactions. The first one is holding 2 substrates, which are most likely going to be monomers, in positions in their active site in which they can react with each other. So this would be having 2 monomers coming together, bonds forming. So it would literally be manipulating them together, shoving them together, allowing bonds to be created, and then the product being one large polymer. The second way that chemical reactions are created by enzymes is the opposite. You're taking one large substrate, which is most likely a polymer, and you're slightly tweaking it so the bonds can be weakened, allowing for the monomers to be stable on their own, and you end up with 2 monomers as your product. So the first one is taking monomers and turning them into a polymer. The second one is taking a polymer and breaking it down into separate monomers.